Welcome back to our deep dive into the fascinating world of artificial intelligence. In our last video, we introduced the transformer model and its revolutionary attention mechanism, encoder and decoder. Today, we're going to pick up from there and drill down further into these concepts, exploring the mathematical relationships, technological breakthroughs, and the brilliant minds behind them. Get ready to embark on an exciting journey through the heart of AI. The journey to understanding how modern AI, particularly the transformer model, processes language is a story of collaboration, innovation, and breakthroughs in both mathematics and neuroscience. Let's start with the pioneers and early foundations. In the 1940s, Alan Turing, often considered the father of computer science, laid the groundwork for artificial intelligence with his famous Turing test, which proposed a criterion for whether a machine can think. In the 1950s, John McCarthy coined the term artificial intelligence and organized the Dartmouth Conference, marking the birth of AI as a field. Neural networks are key to this story. Warren McCulloch and Walter Pitts created the first mathematical model of a neural network in the 1940s, inspired by the human brain. In the 1950s, Frank Rosenblatt developed the perceptron, an early type of artificial neural network designed to recognize patterns. Fast forward to the 1980s and 1990s, Geoffrey Hinton, often referred to as the godfather of deep learning, introduced backpropagation, a method for training neural networks. Yann LeCun developed convolutional neural networks, CNNs, essential for image recognition tasks. The next leap came with recurrent neural networks, RNNs, developed to handle sequences of data like sentences. RNNs process one word at a time, maintaining a memory of previous words. However, they struggled with long sentences due to fading memory. Long short-term memory, LSTM, networks, introduced by Sepp Hochreiter and Jürgen Schmidhuber in the 1990s, improved upon RNNs by using gates to control information flow, allowing them to remember important information over longer sequences. The breakthrough moment came in 2017 when a team of researchers at Google Brain, including Ashish Vaswani, Noam Shazir, Nikki Parmar, Jakob Uskoreit, Leon Jones, Aidan N. Gomez, Lukasz Kaiser, and Ilya Polosukhin, introduced the transformer model in their paper, Attention is All You Need. The attention mechanism allows the model to focus on different parts of the input data with varying levels of importance. Imagine reading a book and highlighting the most important sentences while skimming the rest. The transformer does something similar by weighing the relevance of each word in a sentence to understand the overall context better. So, how does the attention mechanism work? For each word in a sentence, the model calculates three vectors: query, key, and value. But where do these vectors come from? They are derived from the word embeddings of the input data. Word embeddings are numerical representations of words that capture their meanings and relationships. The model uses learned linear transformations to convert these embeddings into the query, key, and value vectors. Think of query as a question, key is something that helps match relevant information to the question, and value as the content. The model asks a question, query, determines relevance using key, and retrieves the content, value. The attention score for each pair of words is computed as the dot product of their query and key vectors. But what is a dot product? It's a simple mathematical operation where you multiply corresponding components of two vectors and then sum the results. For example, if you have two vectors, 2, 3, 4, and 1, 0, negative 1, you multiply 2 by 1, 3 by 0, and 4 by negative 1, then add up the results. 2 plus 0 minus 4 equals negative 2. Higher scores mean more relevant words. These scores are then used to weigh the values, creating a final representation that captures the meaning of the sentence. This allows the model to process all words simultaneously, making it much faster and more efficient. In simple terms, the vectors are learned linear transformations that convert words into numerical representations capturing their meanings and relationships. These vectors are multiplied, and the results are added up to identify the most meaningful and relevant words and ideas. The model then scores and weighs these values to create a final statistical and mathematical representation that captures the meaning of the sentences and ultimately the query. The transformer model consists of two main parts, the encoder and the decoder. The encoder processes the input sentence and creates a meaningful representation. It looks at the relationships between all words and figures out how they connect. This meaningful representation is essentially a mathematical and statistical breakdown that captures the essence of the sentence. The decoder takes this representation and generates the output sentence, using the encoded information to construct the new sentence word by word, ensuring it makes sense. For example, let's say we want to translate "the cat sat on the mat" into another language. The transformer model would break the sentence into words and convert them into vectors. It would use the attention mechanism to understand how each word relates to every other word. The encoder processes these relationships and creates a comprehensive representation. The decoder uses this representation to generate the translation, word by word, in the target language. But how did we derive these mathematical relationships between words? The foundations were built on early neural networks, inspired by the human brain, and advancements in machine learning. Researchers experimented with various architectures and mechanisms, testing their performance on benchmark tasks and datasets. The attention mechanism and the transformer model emerged as highly effective solutions for natural language processing tasks through iterative improvements, trial and error, and empirical validation. This collective effort, supported by open-source AI frameworks and tools, accelerated the refinement and adoption of the transformer model and its variants. The contributions of many brilliant researchers enabled AI to achieve remarkable feats, transforming how we interact with technology today. In summary, let's break down the key concepts again to make them clear. Attention mechanism. Like highlighting the most important sentences in a book while skimming the rest. The model focuses on the most relevant parts of the input to understand the overall context. Queries, keys, and values. Think of query as a question, key as something that helps match relevant information to the question, and value as the content. The model asks questions, determines relevance using keys, and retrieves the content, values. Dot product. A mathematical operation where you multiply corresponding components of two vectors and sum the results. It helps determine the relevance of words. Parallel processing. Instead of reading one word at a time, the model processes all words at once, making it much faster and more efficient. Encoder. Processes the input sentence, understanding the relationships between all words and creating a meaningful representation, which is a mathematical and statistical breakdown of the sentence. Decoder takes the encoded information and generates the output sentence, ensuring it makes sense word by word. The rapid advancement of AI wouldn't have been possible without the immense contributions of the open source community. Sharing research, code, and tools has accelerated innovation and allowed for collaborative progress. Open source work has been crucial in refining models, improving performance, and making these technologies accessible to researchers and developers worldwide. Thank you for watching. If you enjoyed this video, please like and subscribe to our channel at EcoBiata for more fascinating insights into the world of AI, biotechnology, and other topics. Stay tuned for more amazing content.